So let us look at some examples where we calculate limits and infinity and develop some idea. All right, so first examples are polynomial functions. So the graph y equals x is a straight line. So when you take the limit, this limit is simply infinity. And the second example is quadratic function. So when your x gets larger and larger, the function value is unbounded. So this is infinity again. And cubic function will grow as well. So even when you have some big number here, 2020 x squared, the limit is still infinity. Well, this leading term, x cubed, determine the behavior of the function as x tends to infinity. So as you see, those polynomial functions have infinity as the limit. So that means those functions have no horizontal asymptote. So in order for a function to have horizontal asymptote, those limits must be some finite number L. Okay, so next we consider some rational functions. Look at this first example, x plus 2020 over x minus 2020. Well, those numbers, 2020, this number is quite big number, but your x is unbounded. Your x is getting larger and larger, so your x is even larger than any finite number. So for example, x can be million, billion, and so on. So the behavior of the function is completely determined by this term x. So let me circle this. So this x, actually the leading term, which determines the behavior of the function as x tends to infinity. So basically the limit is 1, because as x gets larger and larger, the ratio between two numbers is almost 1. And similarly, for this second function, x squared. So this term, x squared and x squared. So those two terms will determine the behavior of the function, and the limit is 1 again. So when we examine the behavior of functions, we need to look at the leading terms. Actually, limits are determined by leading terms. By leading terms, we mean the term with the largest order, x squared. Okay, so in this example, we have quadratic function and another quadratic function. So here, capital M stands for million. So we have 1 million, negative 1 million, and plus 1 million. Although 1 million is big number, our x can be even larger than that, 1 billion, 1 trillion, and so on. So actually, the remaining terms are negligible. The limit, the behavior of this function is determined by leading terms. So I mean those leading terms. This leading term and this leading term. So you compare those two terms, 3x squared over 2x squared. And the limit is simply 3 over 2. What about second example? So here capital B stands for 1 billion. Although 1 billion is a big number, our x can be even larger than that, 1 trillion, for example. So basically, the leading term in this numerator is x squared. And we have another copy of x squared in this denominator. So we have x squared. And everything else is negligible. So basically, we have negative 1x squared over 10x squared. So as x tends to infinity, the limit is simply negative 1/10. So when it comes to limits and infinity, we need to figure out leading terms, and we need to compare the ratio between leading terms. So let me point out that not all rational functions have a horizontal asymptote. In the first example, we have 2x squared over 3x cubed. When you compare leading terms, we have 2x squared over 3x cubed. Now that denominator grows faster than numerator, this limit is 0. So this function has horizontal asymptote, but look at this. By the way, I meant the middle term is 3t squared, not 3t cubed. So basically we have leading terms, negative 3, t to the fourth, and then 2t cubed. So numerator grows faster than denominator. So as x tends to infinity, this is basically unbounded, but the sign is negative, so it's negative infinity. So now that this is not finite number, this function has no horizontal asymptote. So far we have used our intuition to find limits at infinity quickly. So we compare the leading terms to find the limit quickly. And actually, you can calculate the limit step by step rigorously. So here is the example. So our denominator is a linear function, 3x plus 5, and our numerator is x squared plus 1 inside radical. So this numerator is almost x to the 1. So in that sense, leading term is x to the 1 for this numerator and denominator. So what we can do is to use leading term to rewrite the given expression carefully. So the idea is to divide everything by the leading term. So you divide denominator by copy of x. And you also divide numerator by copy of x. So we divide numerator and denominator by copy of x like this. This denominator is quite straightforward. We have 3x over x, which is 3, and then 5 over x. So to take care of this numerator, we need to replace x by square root of x squared. Then we have x squared inside radical. And now you want to put them together to get better expression. So once you put them together, we have x squared plus 1 over x squared, and the same denominator, 3 plus 5 over x. Now that your x tends to infinity, this 5 over x is going to be very small. Actually, this will be gone. And similarly, you want to somehow rewrite to find the limit of this numerator. So inside radical, we have 1 plus 1 over x squared. As you see, this 1 over x squared is going to be very small as x tends to infinity. So basically we have square root 1 over 3 or 1/3. So this is how to calculate the limit carefully using the leading term. Again, the idea is you determine the leading term and you divide everything by the copy of the leading term. Let me point out that when your x tends to negative infinity, things will be quite different. So expression is the same as before. So the leading term is copy of x. So you have to divide everything by x. So this limit is going to be numerator over copy of x, or x squared inside radical, and 3x plus 5 over x. So that's what we want to do. But here, now that our x tends to negative infinity, our x, it's reasonable to say x is negative. This is quite important observation. Now that x is negative, look at this expression. No matter what it is, we have positive symbol. The hidden symbol is positive. I mean, hidden sign is positive. So this is something we need to change. So this implies your x is when x is positive, this is true, but when your x is negative, we need to put extra minus symbol like this. So that's why we need to have this extra minus symbol. So the remaining calculation will be similar. So after simplifying this denominator and numerator, we will have but remember, we have extra minus there. So after taking the limit, we have negative 1/3. So even when you have the same expression, the limit is not the same. So this limit as x tends to negative infinity is not the limit of the same expression as x tends to infinity. So depending on the sign, you need to be careful with this negative, extra negative.